Hi guys. So this is a direct continuation of activity 3.2. The two main goals for this activity is to be able to, one, take a set of data like the one that we're going to look at right here in a second, and be able to, first we already know to be able to figure out if it's linear or exponential, but then once we know it's not linear and we know it's exponential, how do we find that either growth factor or decay factor by looking at the data? Because that's one goal. Our second goal would be able to write a full equation in this form that we see right over here, y equals a times b to the x. So in the last couple activities, we looked at exponentials that said y equals just b to the x. So now we have, and it's not that we are changing the exponential form, it's just that in the last examples that that y-intercept, was 1 all the time, and so we just didn't have it in the equation. So now it's a matter of, well, what happens if that initial value is not 1? Okay, so let's look at this data. This set of data represents the number of cell phone users in millions for each year. Okay, so each year is starting at 2000, so that's our initial here. Okay, so in general, when we write our equation for this eventually, we want, if x is 0, we want it to come out to be this value right there, okay, because that's our initial number of cell phones in that initial year. Okay, so the first thing we're going to look at, is it linear? Okay, so we're testing linear to see if it's a constant rate of change. Since our years are all 1 apart, it's very easy to find the difference in each one of these number of cell phones to see if it's constant. And if we do that, we find out, no, it's not a constant rate of change. Not a constant rate of change, and that's what it would take to be linear. So now we're looking at our next type of function to see, okay, now is it exponential? So to be exponential, it means, okay, again, these are all 1 apart. All my x's right here are all 1 apart. So that's easy for us to figure out. Okay, so am I multiplying by the same thing each time to get my next output? Okay, so this table down here is actually just having us figure out, okay, from 2000 to 2001, what did you multiply to get from 109.48 to 128.37? So we're really, this is what we're actually doing. We're really taking 128. I know they wrote it right there, but I just want to show you what their calculator's dividing this out and seeing what you get. Okay, so when you divide that out, you get 1.09. Oh, sorry, I was looking at the wrong one. That one right there is 1.17. So it really means to get from 109 to that 128, we multiply by 1.17. So it's growth, okay, it's increasing, and we'll figure out in a little bit what it's increasing by, but being over 1 means I'm growing. If I do the next thing, okay, so the next part, if I do, okay, what is 140.77 divided by the 128.37? What is my growth factor for that? And that comes out to be 109. Just ignore my phone ringing, I'm sorry. So the next one right here, if I kept doing, this is 1.11, this is 1.16, 1.14, and 1.12. Okay, so each one is a growth, and it's not exactly the same. In real life, data is rarely going to get us the exact same amount, but it is pretty consistent. Okay, so what do you notice about the values on the table? The growth rate is pretty consistent. And if I kind of averaged all that out, we would find that it's about 1.13. Okay, so when that's a growth, when that's an increase, a growth factor, the 1, what's past the 1 is telling us what percent it's increasing by. So when I multiply something by 1.13, it means the 1 is the initial value, and then the 0.13 is how much it's increasing by. So this is increasing by 13% each year. This is the same way you would do tax. You know, if I had bought an item for $100 and it was 6% tax, I could multiply it by 1.06 and get my total cost. Not just my tax, but my total cost. Okay? All right, so now, let's see. So here's what we're talking about right here, okay? They're talking about successive ratios. These are ratios that we just found in that table. And if they're constant, then we can call this an exponential function. Okay, and if it's greater than 1, this is what we talked about in the last couple activities, it's growth. If it's between 0 and 1, it's decay. Okay, so can this table right here? Yes, this table right here can definitely be exponential. Okay, the ratios are pretty constant at 1.13. So we can say that we can use an exponential equation for this. So we just actually answered the next question. Okay, what is the growth factor? Okay, so for this one, the growth factor is at 1.13. Okay, so each year that goes by, if we multiply the previous year by 1.13, that's how we're going to get the number of cell phones. Okay, so what we're going to do here is we're going to use our growth factor to see what ends up coming out, and we'll compare it to see how close we are to the original data. So each time we're multiplying the previous year's cell phones by the 1.13. Okay, so we're putting it in kind of what we probably would call like expanded form, that first column. Then I'm going to write it as an exponent. So this is, we're multiplying it by 1.13 only once, because we're only t equals 1 year past that initial. And then we would get 123.71. So if 2 years have gone by, then we really have to do 1.98 times 1.13 times 1.13. I probably should use parentheses here because my dots look like decimals. Okay, I have to multiply it by 1.13 to the second. And there's my initial one still in there. Okay, and then this comes out to be 139.8 million cell phone users, and that would be 2002. So let's do the next one. So that means I have to do my initial, my initial times 1.13. Now I'm doing it 3 times because I'm 3 years past that initial year. So I would write it as 1.13 to the third times, again, don't look at this initial one. Okay, we didn't have the initial one in the past couple of examples because the initial was actually 1, so we didn't really see it. And this comes out to be 157.97. So these are not going to be exact on what the table was in the page before, because remember that 1.13 was kind of an average of what it was doing every year. Okay, but now that we have that, we can write our equation and we can start to predict other values. So our next thing is to use this pattern and write an equation in this form right here. Okay, so N of t is going to be the number of cell phones in whatever years past 2000 we are. Okay, so that that one's our initial amount, so that's going to be our 109.48. That's in 2000, how many millions of cell phone users there are. And then we have our growth factor to the t. So I just want to come over here for 1 second to show you how it does work out. If t were 0, meaning we're at the initial year of 2000, I just want to show you that by having that initial in the beginning, okay, if I raise that 1.13 to the 0, remember anything to the 0 is 1. So I do end up getting my 109.48. Okay, so that's my initial amount. And it's also my y-intercept. Okay. So what's the practical domain for this one? Well, the year of 0 is our initial one. Okay, we can't have negative years for this. And this one, I think the original data went up to 2006. So we're going to say this function really works from 0 to 6. Anything outside that we can predict, but we don't really know how accurate it is if we do it as extrapolation. Okay, unless we know the pattern that's going to happen past those years. So we're going to do a quick graph of this. So I have my graph set up. So again, you should stop real quick, set up your graph. You can do one of two things. You can practice graphing this on the calculator, or you can take a couple points that we have up from the table and sketch it like that. Okay. So my initial value is that 109. So this is kind of a little bit of estimation, but it's going to look like something like this. So here's my function. We can see it's increasing, okay, which we learned before because our b is over 1, so it's definitely an increasing function. We're only seeing part of it because we're only graphing what makes sense for this domain. Now this graph does keep going to the left if we were not looking at it in this situation, okay? But for right now, we're looking only from 0 to 6 because that's the years that we know this is defined for. Okay.